Hi, everybody. This is Dr. D here. It's good to see you all. Today, we're going to talk about the 4 steps to solve all distribution problems. Before we get into them, I do want to say it is always possible to solve these faster than the approach that we're going to take. But we're not going to find a shortcut. We're not going to try to jump right to the answer. And I want to be clear about why. It's not that I have a problem with getting answers faster. It is that the purpose of solving normal distribution problems is almost never to get directly to the solution. Because very rarely are we going to find problems like this per se in a real and complicated situation. Those problems are going to be more complicated than the ones we're dealing with here. And what we're working on today is the mechanics of some of the underlying dynamics. We have some assumptions that are unrealistic, but they simplify things nicely and they make it easier to learn. So that when we get to the more complicated stuff, we understand the mechanics of some of the stuff that's working in the background. We hopefully have that on a more intuitive. So I just want to be clear, we're not going to skip steps. I'm never going to skip steps, but we're going to work through these in their full glory so that we can develop the skills we need. To start things off, though, I do want to read a question and motivate. So, for borrowers with good credit scores, the mean debt for revolving and installment accounts is $15,015. Assume the standard deviation is $3,540, and the debt amounts are normally distributed. So that's positing a particular shape of the world. The world looks such that we have borrowers with good credit scores. That's a population of individuals, and they have some value called their debt. Each one has their own debt. There's many different unique and individual borrowers with good credit scores. But if we took them all and averaged all of them, the mean debt would be $15,015. But they're not equal to each other. Some have more debt, some have less debt. How do we measure that spread outness? Well, standard deviation is one way to measure it. And the standard deviation among all borrowers with good credit scores is 3,500. What we want to know is, what is the probability that the debt for a borrower with good credit is more than $18,000? Now, who would want to know this? Well, it's possible that the person who would want to know this would be like a loan officer at a bank. Because you can see 18,000 is more than 15,050. It might be quite a bit of debt. Nonetheless, these are borrowers with good credit scores. So if somebody comes into the bank, you might want to know, okay, so this person has more debt than usual, but is it like a little bit more debt than usual, or is this a really unusual circumstance? If it's a really unusual circumstance, maybe it's above your pay grade to make a decision about whether this person's a good debt risk. Maybe you need to call your manager. Because either maybe this person's a bad debt risk, but their credit score just hasn't adjusted yet, or there's some subset of people who have good credit who maybe they have a large inventory because they run a small business, but they're an individual proprietor, so they maintain it as a personal account. In which case, that might be a large customer. In which case, again, you might want to call your manager. But you really need to know, like, how rare is this a weird case, or is this just a somewhat unusual case? So that's why this probability would potentially be important. It would be important because you need to know, you might need to do something with that information. Okay, so how do we solve a problem like this? Well, to solve normal distribution problems, what we want to do is we want to model them. So how do we model and work our way through them? Well, the first thing we're going to do is we're going to turn our question into a picture. This is always going to look pretty familiar. Been following along so far, then you've seen me draw more than a few of these. If your drawings of these are terrible, don't worry. Mine are sometimes terrible too. They get better over time. That was not great, so let's try another. That's it's a normal distribution. It's going to have a mean. It's going to have a standard deviation. I'm not doing this specific situation. There's going to be some value of x, and there's going to be some area. Okay, so that's the first approach. There are 4 of these things you see that we'll get. We'll get 3 out of the 4. The question will always give us 3 out of the 4 if it's a normal distribution. Mu, sigma, x, where x is some value of whatever the variable is we're measuring. In this case, it's a debt. Debt in revolving installment accounts, to be precise, and p. So you always get 3 out of the 4 of these variables. And then the question is, what is the 4th, right? These 4 characteristics of a population, right? The average of the population, its spread outness, some value of a variable, and then some likelihood. They are logically required, right? They're connected to each other such that if you have three of them, the fourth one is a logical necessity. So three of these logically necessitates the fourth. There's only one possible value. And so step one is to turn this question into a picture of a normal distribution. Now, what we've learned about in the past is that there's an infinite number of normal distributions. They vary based on their mean and their standard deviation. What we are going to do is we're going to measure these based on we're going to relate it to the standard normal distribution. So we have one specific normal distribution called the standard normal distribution that has a mean of 0 and a standard deviation of 1. That is always true. So, once we have this, what we now do, essentially, is we say, okay, so that's the value of, or that is the system we're analyzing. What we're now going to do is we are going to draw another distribution underneath. But this one is not the x distribution. This is the z distribution, which has a mean of 0, standard deviation of 1. And then that x that we identified from the first step is going to have a corresponding this is our z value, not 0, but the z that corresponds to x. And then it turns out that this area P will be the same as that area P. So mu is 0, sigma is 1, and then the z corresponds to that x, and the p should be the same. You'll know that you're done with step 2 when you have 3 out of the 4 here. Right? Now those are always going to be mu and sigma, because those are always known. It's always 0 and 1. So the question then is x the question mark, or is is z the question mark? Or is p the question mark? One of these is going to be unknown by the time you get to the end of step 2. At the end of step 2, you'll know, okay, so now we've taken this normal distribution problem about some x distribution, we've converted it to a question about a standard normal distribution problem. Which is good, because I have 2 other videos that I already taught you about how to find things in the standard normal distribution. And if you've practiced those and you know this, we are going to, by the time we get to step 3, you can see that we either know z or we know p. And so step 3 is use z to get p, or to get z. And so in this scenario, what we essentially are doing is either we have an area, in which case we need to relate it to get the z, or we have a z, in which case we need to relate it to get the area of some kind. The trick here is we're either going to use norm.s.dist, and that'll get us from some z to the area to the left, some area p, or we use norm.s.in, which will get us from p to z. Sometimes we have to manipulate things a little bit to get to a place. This is all in Excel, by the way. These are the Excel formulas. Sometimes we have to manipulate things to get the correct p to be able to spit out the z we want. And if that's the case, that's part of step 3. But once we've gone from one axis, one side of the axis above it with probability, down to the underside, or vice versa, then we are done with step 3. And then we're on to the final step, step 4, which is, I admit, a bit of a cop-out in terms of which is to answer the question. We reread and answer the question and make sure, usually at this point we're a little bit in the weeds, but we have everything but maybe 1 or 2 things. So maybe we have the area, but it's not exactly the area we need. Maybe we have z, but we actually need a dollar value. And so sometimes we'll go from p to the correct area, or go from z to the correct, the requested value. Maybe the question wants a mu or a sigma or an x, and we have to use a z-score to get that. At some point, the other thing we haven't talked about yet that we would need, at some point we're going to, and often it's here, but at some point we need to use the z-score formula, which looks like this. Z equals x minus mu x sigma x. And that will be the 4th piece that you need. Right? So sometimes you need to do that in step 2, sometimes you need to do that in step 4. But at some point, we're going to need to do that. And so that's something to keep in mind. Okay, now that we know the 4 steps, just to recap, they are turn your question into a picture, relate it to the standard normal distribution, use z to get p or p to get z, and then answer the question. We can answer question 3a here. So let's start at the start. 3a. Again, we've got borrowers with good credit scores. We're assuming that they are normally distributed. This is the value of x. Distributed. Average value, call it mu x, 15015. Sigma x here, standard deviation of the population of all these borrowers, is 3,540, and these are measured in dollars. And then part A says, what is the probability that a debt for a borrower with good credit is more than 18,000? That more is critical. It's a directional word. So 18,000 is larger than 15,015. So 18,000 is going to be right here. I'm going to skip that so I can demo it. 18,000. The probability that we would get somebody at 18,000 or higher is going to be the size of this area over. That's our question. And that is the end of step 1, because we have 3 of the 4. We have mu, we have sigma, we have x, and we don't have some area. Area, that's the 4th thing, is the thing we need, and so we need to find that. And that's the end of step 1. Step 2 is to relate this curve to the standard normal distribution. So, I draw another distribution down here. This is the z curve. Z is equal to 0. Sigma z equals. We've got some value of z that we don't know yet, but if we find that value of z, we can use it to find this area here, hopefully. This area, which is now unknown, will be our unknown. Should be, if we did it right, should be the same as this area here, right? Essentially, we're using the z distribution as like a yardstick. We're using that z to measure this. Okay, so in order to do that, to find that z, we're going to need to use the z-score formula. And we can use this whenever we have 3 of the 4 values. So x minus mu x divided by sigma x. We have x, that's 18,000. We have mu x, that's 15,015. 18,000 minus, oops, that's 1,800. 18,000 minus 15,015 divided by 3,540. Not from behind my head. That's going to be the value of z. That's how we're going to calculate it. Okay, so switching back to Excel, because Excel is where I'm going to do all my calculations. I want to make sure that I label my work carefully. So I've got mu x, 15015, sigma x, 3540, x, 18,000, and now I'll have my z numerator. That's going to be x minus mu x, and then my z score, z numerator, z is going to be the z numerator divided by sigma x, 0.84322. Now, if you watch my previous videos, you'll remember that the z-score is the answer to the question, how many standard deviations away is this value of x from the mean? And it turns out that this is 0.843, give or take, standard deviations to the right. So, are we done with step 2? Well, we have 1, 2, 3, and 1 unknown in the z distribution. That's what we said would be the determinant as to whether or not we were done with step 2, and we are. Okay, now step 3 is to use z to get p or p to get z. We have a z-score, and so we can use this z-score to find an area. Now, if you remember learning about the inverse standard normal distribution, what the inverse standard normal tells us is the area to the left of z, which is going to be this big ol' area, anytime you give it a z. So Excel, very quickly and straightforwardly, will tell me how big this area is. So let's do that. The formula here, I wanted to show you these formulas. I didn't want to leave them hidden. So let me just demo, show you where these are so you can see them. Okay, so let's do area to left. That's going to be norm.s.inv, returns the inverse standard normal cumulative function. And then I just need to feed it to z. And it should give me a number larger than 0.5, right? Because this total area is 1. And we're using up this entire left half and then some left over. Oh, I did it wrong. It's not norm.s.inv. It's norm.s.dist. What am I saying? The area to the left is norm.s.dist. Apologies. Norm.s.dist. There we are. And we need it to be cumulative because we don't want the height of the curve. We want the area to the left. So norm.s.dist, put in our z-value, put 1 for cumulative to give it the area under the curve. And that's correct. 0.80045. I knew it was wrong immediately because it was larger than 1. It can't be larger than 1 because it's a probability. It has to be greater than 0.5 but less than 1. So this area is 0.80045. And that is the probability. If the question said, what's the probability that the debt for borrowed with good credit would be less than 18,000, that's what it would be. It'd be 0.80045. Now, what's the area to the right? Now, that's the end of step 3, right? We use z to get p. And this is the probability that z is less than or equal to 0.843, which is the probability that x is less than or equal to 18,000 equals 0.8045. Step 4 is to answer the question, which is not to find the area to the left, but to find the area to the right. So how do we find the area to the right? Well, we know this green shaded area and this pink shaded area must add up to 1. So this is going to be equal to 1 minus 0.8005, which is going to be roughly 20%. The area to the right, get this formula so you have it. Area to the right is just going to be 1 minus this. And it's 19.955%. That's the correct answer, right? That's the answer to what is the probability that a debt for a borrower with good credit is more than $18,000. Well, the area to the right here in the z-curve, this is 0.19955. And then because we engage in a careful process to produce this, that means that this also is 0.19955. So, what is the probability that the debt would be larger than $18,000? Almost 20%. Now, is that likely? No. But is that so unlikely that you should hit the red button that says stop all business and then wait until your manager tells you what to do? Probably not, right? It's a significant thing, but it's not the end of the world. It would be like, oh, okay, this doesn't happen every single time, but 18,000. Okay, so what can we say? Well, we've got a few other problems here that require the same setup, and I'm going to just kind of help you get them set up. As you move along, getting set up becomes the hard part because the mechanics become easier. But while you're still learning the mechanics, let me help you get set up. 3B has the same setup. They all actually have the same setup for the beginning because this is just a drawing of the population. So actually, let me copy this drawing, and now I can reuse it. 3B is asking about the probability that the debt for a borrower with good credit is less than 10,000. 10,000's over here. And they want to know what's this area going to be. And you would go through the 4 steps. 3C, very similar. But instead, the area that they're looking for is between 12,000 and 18,000. And so it's going to take a little bit of doing. You're going to need to find 2 z-scores when you do it, and that will mean you need to find 2 tails and subtract them to find the difference. Very similar to some of the stuff we did in question 2, the between ones that we did in question 2 earlier. And then 3D is very similar, but now it's just asking no more than 14,000. So no more than 14,000 just means 14,000 or less. One of the interesting and complicated things, maybe not super complicated, but can be sometimes confusing, is that the difference in this scenario between this and less than or equal to 14,000 is 0. It turns out that whether it's less than or equal to, those numbers turn out to be identical. Why? Because the chances that someone is going to walk through, if you have a large enough population, the chances that somebody's going to walk through the door with 14,000 and 0.000000000 cents is treated as 0, right? It's just too fine a line for somebody to come in with exactly to the penny. It's close enough to 0 that it makes no difference. So anytime we have a continuous probability distribution, the value added by including the equal sign in the probability is essentially 0. Okay, so those are the 4 steps that we use to calculate, to solve normal distribution problems. Turn the question into a picture, relate it to a standard normal distribution, use z to get p or p to get z, using the dist and in functions, and then answer the question. Alright, now what I do want to say, one, we only did one kind of question where we found an area. I'm going to leave it to you, and maybe we'll talk about it in class, or maybe I'll make another video at some point. What happens when they give you an area, and then you have to find an x, right? That's a slightly different kind of problem. Not super different, but it's slightly different. The last thing I want to leave you with is assumptions. So we made three terrible assumptions anytime we're using normal distribution questions. They're fine in that they make the questions easier, but they're bad in the long run. So the first thing we assumed was in each of these cases we assumed that x was normally distributed, and that is just not generally true. There just aren't that many things in the world that are normally distributed. So that limits, if it turned out that we were limited to those cases, that'd be bad. Fortunately, we're not, and next time when we meet, we'll talk about why. The second assumption is that we assume we know sigma x, right? We labeled it as 18,018. If we knew sigma x, we wouldn't need to do statistics. The whole point of statistics is inferring population values based on our samples, right? We can't see the population. That's why statistics is valuable. So why are we assuming we know mu x? Well, to understand the mechanics of this, right? It's not a great assumption, and we'll get rid of it as soon as we can. But we have to learn some more mechanics first before we can abandon it freely. The third terrible assumption is assuming that we know sigma x. Again, if we knew, we would have to know mu x to be able to find sigma x. That's how sigma x is calculated. So that's another bad assumption that we will abandon as soon as we can do so responsibly. For now, we're going to take these in order. Next time, we're going to get rid of this one. The next time, we're going to find out what happens when we get rid of this one. And then shortly thereafter, we'll find out when we get rid of all 3. When we get rid of all 3, right, then what we're doing is we'll be generating new usable human knowledge. But to do that, we're going to have to relax some assumptions and figure out, like, okay, so what happens if we get rid of them? And so that's where we'll start next time. We'll talk about what happens when x is not normally distributed. All right, thank you all, and I'll see you next time. Bye.